I said we're done. We're done with chapter 10. We still have chapter 11 to talk about. Lecture videos for chapter 11 will come soon. They're actually relatively short, so that's good news. But I've been talking for a while and my throat is getting kind of dry and scratchy, so I need to take a break and record videos later. The last piece of the puzzle in chapter 10 is to sort of synthesize what if we have rotational motion plus linear motion. Imagine that I have a bicycle wheel and I'm holding the axle. The wheel is rotating, and as I walk this way, holding the axle, the center of mass of the wheel translates, moves linearly, while the wheel itself is rotating. So it has both kinds of kinetic energy. It has the linear kind associated with the center of mass, and at the center of the speed with which the center of mass is moving across the screen, and the kinetic energy associated with its rotational mass distribution rotating with angular velocity omega. So we could try to talk about the total kinetic energy if the object is doing both. We might need to talk about the velocity of its center of mass and its moment of inertia and its angular velocity. Note that this is m total, the total mass that's moving to the right. Well, moving. All right, there's a very particular kind of combinatorial motion that I'd like to say a little bit about, and that is if we are rolling along a surface. We go from here to here, and if this is the same point that rolls around and comes back to the ground, then we've gone, this distance is the circumference. If it takes some amount of time t, that's the speed with which the entire hoop, this circle, moves across the board. It takes capital time t to go across a displacement. The center is here at the center. It is a circumference away from the thing, and it's moving this fast, it must be. Okay, but in order to make a full rotation in an amount of time, capital T, omega must be 2 pi over t. And now it looks to me like the velocity of the center of mass of this rolling thing, 2 pi over t, is omega times r, the radius of the surface on the radius to the surface on which it's rolling. This is special. Omega r on its own is related to the tangential speed of a thing that is only rotating, right? If I pick up the axle of that bicycle wheel and it's rotating, and I ask about a point on the tire as it moves around in a circle, how fast is it going through space? This fast. This alignment, this equality here, says that not only is that true, not only is a point on the rim of the wheel moving this fast, but the velocity of the center of mass of the entire wheel as it rolls is the same. And that's pretty cool. This is the smoothly rolling condition. And if we wanted to talk about the acceleration, we could do that too. The acceleration of the center of mass in linear motion is related to the rate at which the rotation increases. Smoothly rolling without slipping. So there's two kind of keywords for that. Smoothly rolling and rolling without slipping. Whenever we see that, it means this is a true thing. that's the, I'm going to include one more video that's based on a PowerPoint that goes with the chapter 10. I'll include the PowerPoint as well, that talks about the last little bit of chapter 10, and that is chapters 9 and 10. Look for chapter 11 coming soon. Thanks, everybody.